All right, so my name is Miloš Krstić. I'm leading the department System Architecture, but I'm also here presenting the space activities of IHP and the current status of which we have of radiation hard evaluation for space evaluations. So we are working already for plenty of years on the radical technologies for space and extreme harsh environments. Maybe some of you is already aware that we have already one process, and this has been mentioned already by Andreas and René, the process photomicron SGB25RH, which is fully evaluated against ESCC standards, and it is EPPL listed. We are working also on now more advanced process, which is SG13RH, to fully evaluate this process as well and to provide the EPPL listing. So let's start with introduction. So what are the specific of space applications? So there are several of additional requirements which come together with the space applications. So on one hand, we have the temperature stress. So we have usually for the devices which are needed in space, increased temperature range. So usually we are addressing minus 55 degrees up to plus 125 degrees. So this is higher even than the military standards. Then we are having additional challenges with the radiation effects. For example, the effects such as total dose effects, which are affecting the parametric behavior of the transistors, or the single event effects, which can cause the upsets in the logic, or even single event latch-up, which can permanently damage the device. Moreover, we are talking very frequently about the long time missions. So it is frequent case that you have the missions which are 10 years or even longer planned, and you have to ensure the availability and reliability of the devices because in the space it will be very difficult to make any sorts of replacement, repair, or something similar. So we are here also not discussing the space environment only. Similar requirements are also appearing in some other application areas such as medicine, nuclear physics, or filing logistics. So what are the benefits of IHP in this context? So in the space environment, we have the strong need for RF ASICs. So there are lots of components which are required in order to address, for example, communication in the satellite market. So in order to implement this kind of circuits, BiCMOS could be a very good solution. Moreover, when we are talking about the space, we are talking about the niche markets. So you will rarely produce millions of chips for space market, and frequently you may need even just a single ASIC for some special measurement instrument. But in general, the volumes which we are here discussing are in the order of what IHP can definitely address. Moreover, IHP is a fully European technology, which is also strategically important. We know all the restrictions on export which are related to the space-related product, and one important relation is ITAR from USA. We have the ITAR-free technology, and this could be also very much used. And we are also would like to address these extreme environmental conditions, and I will show you a couple of results of what we have achieved until now. So the target for us is to work together with the agencies. So even the best results will not bring you to the market if you don't have the support of the related agencies, and for us are relevant DLR as a German national agency and European Space Agency. And we have focused on the two technologies at the moment. So on one hand, SG25RH, which is kind of a derivate of our known process SGB25V, and SG13RH, which is compatible to the process SG13S. So we have to limit at the moment the scope of our space approach because the costs of the evaluation are significant, but in the future, depending on the industry demand, we could consider also the further technologies. So our target with this is to develop the related design kits, which are providing radiation hard or radiation tolerant application of these technologies. Also to work with ESA and evaluate the technologies and bring them to the state that they are listed on the ESA EPPL listing. This is ESA preferred parts list. And also to offer the access to these technologies to the customers and to the research. So this slide is familiar. It was shown by René already. These are the flavors of technologies which we are currently supporting at IHP. And what we can see is here the SGB25RH as the Radhard variant of our known process SGB25V, and SG13RH, which is the Radhard variant of our known process SG13S. So in case of SGB25RH, so this is a frozen process, frozen PDK, the technology is evaluated already. In case of SG13RH, we have stable PDK, we have the early access to the technology, but it's not still considered as qualified because we are still working on the evaluation together with European Space Agency. So let me go just through the very short status of both technologies. With respect to the quarter micron technology, we are addressing the radiation hardening by design. So there are plenty of approaches. There are also technological approaches to address the radiation hardness. In our case, we will see some features of our technology, natural features of our technology when it comes to the radiation. However, some effects needs to be addressed by design and by PDK, and this is what we did. And within the process which we had and the projects together with DLR, we have been evaluating the capability domain, and we have developed the test vehicles such as TCV, DEC, and RIC. So these are generally for the people working in the space area the required test vehicle to address the technology, to address the PDK, and to make some evaluation of the representative integrated circuit. So we have the EPPL listing since August 2018, and we have already some relatively significant number of customers which are actively using this technology. We are continuously maintaining our process identification document, and if you need some more information, do not hesitate to contact me or some of my colleagues. With respect to the 130 nanometer, we are still working on this. Radiation assessment has been performed. I will show you some representative results, and we are working on the evaluation process which will address the reliability of the technology. So yeah, this is just an illustration of the EPPL listing of SGB25RH, which is present still since 2018. So let's see a bit more results of the ongoing evaluation of SG13RH. So, as mentioned already, the baseline for SG13RH is SG13S, standard commercial technology. I will not repeat the features of this technology. I think this was already introduced by Andreas and René. But on top of this, we have developed also the radiation hard by design libraries, which includes some specific analog devices, for example, the ELT transistors, which are tolerant to TID effects, and also some digital libraries, which are also addressing the problems of single events. Moreover, we have also the PDK, which is addressing some special design rules when it comes to radiation hardness on top of this. So this was the activity which was promoted by DLR, and the radiation assessment has been performed already, and this project has been successfully finished. In this process, we did single event testing according to ESCC standard. We have performed also total dose tests according to ESCC standards, and we have performed the draft definition of capability domain and draft of the PID also according to relevant ESCC standards. So the remaining part to get this technology into the EPPL list of ESA is to perform the evaluation testing of the endurance, again in accordance to relevant ESCC standard. This activity started in 2019 within the project which has been sponsored by European Space Agency. But we started this project already with a very high confidence, because this endurance evaluation is, of course, the additional check of our technology, but for the commercial process SG13S, we already performed the endurance test for commercial standards. So in a way, we are about to repeat the similar things for ESA and make also some few additional tests more. So this is the status which we have at the moment there. We have developed the corresponding test structures, including this TCV, technology characterization vehicles, including the selected active and passive components from the SG13 flow resistors, CMOS and bipolar transistors, and metal lines, and they are about to be tested for the endurance. Then we have been working on the several test structures which assemble all together DEC, dynamic evaluation circuitry. So then this is already one complexity above. So we are addressing not anymore the individual components, but a bit more complex structures. So ring oscillators, shift registers, band gap reference, VCO, then the single transistor amplifier, and trying to perform more detailed tests of what happens in these complex structures based on the stress activity. And then we have the representative integrated circuit, which we are also developing and which is also taped out, which includes the fractional and phase loop working around 31 GHz. So this is something which is currently being produced and where we soon expect to start with the packaging and with the tests. So this is a test program which is planned, which includes some thermal characterization at the different temperatures, storage testing, and then the endurance tests up to 2000 hours. So this is already quite significant amount of testing on the high temperature. similar tests will be performed also on the deck, including terminal analysis, and then also the endurance testing and the constructional analysis, and we will do also the endurance tests up to 2,000 hours on the representative IC. So let's see a bit more details of the status of the PDK for the relevant processes. So we have here the summary of these two processes which we have. So as known, both processes are commercially qualified. Quarter micron is commercially qualified in 2010, SG13 in 2014. And they are very stable from the technological point of view. We have performed the analog radiation assessment in both cases, so you can see that the HBTs are naturally very rad hard when it comes to the TAD effects. We have measured here up to 800 kilorad, no effects, even the low dose effects, there are none. We have some issues with NMOS over 100 kilorad with the TAD, but for this we have the ELT NMOS, which are providing us at least 550 kilorad. For 0.13, we have measured even over 1 megarad, and we have no problem with the HBTs. And with the CMOS, we will have some issues over 50 kilorad in case of NMOS devices. We have the ELT devices instead, which are tolerant until 900 kilorad. So for quarter micron, the PDK is completed. It includes the digital libraries. It includes the aging modeling. It's available under NDA, and the export has to be checked as well. It's based on the two different digital libraries. So one is based on the Dolphin cells, standard cells, which are extended with special radiation hard by design cells from HP. And we have on top of this also Saphirion smaller library, which is tested only for SUs and SLs. The assessment has been performed on the digital cells as well. So we have tested for TAD. We have seen the minor increase of the leakage current up to 300 kilorad. So I think, if I remember correctly, something like 10% increase of the leakage current, which is not something really significant. And we have the single event latch-up threshold, which is at least above 65 megaelectron volt per square centimeter per milligram. And we have also rad-hard flip-flops, which are at least having the threshold over 30 megaelectron volts. When it comes to SG13S, this is the PDK which is in the early access in development, but we have already the library which is available. We are working on the aging modeling, so this will be also available very soon. And you can get the access by signing the NDA and after checking the export license. So we are owner of this library fully. So this is a library of 90 cells. We have tested for TAD. There were no big issues as similar as for quarter micron. And we have the single event latch-up threshold above 60 megaelectron volt and single event upset threshold, which is also, we have some cells which are in the full range of the tested area, which we didn't show any upset. So when it comes to the endurance, for quarter micron, this is fully completed. As mentioned already, we have very stable HBTs with no low drifts, and we have the lifetime determination of approximately 20 years. In case of 0.13 micron, This is the ongoing process. We plan to perform this test during 2021 and to finish it in 2022. However, you have the access to our commercial SG13S test data, so you can check the reliability tests which have been performed there in order to make your judgment about the reliability of this process. So just at the end, just a few results and ongoing activities. So one of the activities which was very interesting for several customers and for European Space Agency as well is the development within the EU Marilyn Robin project, which was 25 gigabit per second transimpedance amplifier and 40 gigabit per second VCSEL driver, which could be channel independent digitally controlled via SPI, which also offer power on reset circuit. And you can see some measurement results of both TIA and VCSEL driver at the relevant performance levels. Here are some heavy ion tests which have been performed. I think also quite nice results. So they have been performed on relatively high or very high LEDs of 32.4 megaelectron volt and 62.5 megaelectron volts. There were no latch ups detected, and you can see still relatively solid bit error rate, which can be achieved especially for transimpedance amplifier, also under the radiation. And we are now working on finding a solution and financing for turning this into product and making the qualification of those devices. There are also some ongoing activities. I would like to mention some space networks on the European level where we are involved. On one hand, we have the collaboration which is called Space Region, which includes the border lines of Germany and Poland. So we are working together with a Polish partner to establish joint space activities. On the other hand, we have the Elixir network. So this is again one European network where we are working together with a Serbian partner, with Tyndall from Ireland and University of Granada on the issues of radiation, ionizing radiation effects. Finally, we started last year the development of our Rad-Hard microcontrollers for space applications, which is based on the novel instruction set architectures and complete tool chain. So finally, we have also lots of interest already from the industry for some microcontrollers. So I hope in a few years we will be able to present something along those lines as well. So what are the plans for us? So first target is of course the finalization of the ESA evaluation for 130 nanometer, and this project should be followed immediately with the EPPL listing of the technology. So we think that this should be finished somewhere in 2022. And depending on the demand, we can consider also some further IHP technology for the evaluation. When it comes to the other development, as said, VCSEL driver qualification is something where we are very interested in looking for a partner there. And there are also some other developments which are ongoing. I mentioned Rad-Hard microcontroller within Moral EU project, but also it's worth of mentioning Rad-Hard ADC and Rad-Hard service, which we are developing with our partner Archimea. So there are also several other projects which are under qualification or qualified from the industry partners using IHP technology. So if you need some more information about that, do not hesitate to contact me. So thank you very much for your attention, and feel free to contact me or ask me immediately with some questions.